So, hello everybody. Welcome to this new tutorial. In this case, we're going to see what we're going to do today are the famous 3D GANs. So in this first part, we will go over data generation because we have seen, there are a couple of old tutorials and things that you can of course find on the internet. And when we talk about data generation, sorry, I have like a couple of things open. So for example, you go to like 3D GAN original paper, you will see this website that probably is the most famous one, where the original paper was called Learning a Probabilistic Latent Space of Object Shapes via 3D Generative Adversarial Networks. Basically, it was a ShapeNet. It was trained on ShapeNet on voxelized objects. And even though the code is available, this is old code. This is really old. Like, I mean, it's if I remember correctly, like 2018, 2017. And it has a couple of problems that it was written in Torch, not PyTorch. It was, the dataset is in the math folder, so it's MATLAB. And even though there are other 3D GAN approaches, TensorFlow, if you look, like, you can find like many, like 3D GAN is basically like the same implementation. And there are a couple of things that sometimes you see that they just don't work because they don't focus on the data generation, because they don't basically like code, especially for like this type of things that are experimental and there are no like much new research about it. Libraries and things that you're using are deprecated, so they are no longer supported, or there are like things that already changed. Hardware is an issue. If you don't have like a good GPU to train you cannot do this. And so there are some things that you can do on Colab, and this is what we will do. There was recently, and it was like a nice coincidence that Runjia Tan did a workshop on this like a couple of weeks ago. This was a video that that I've been preparing, or a series of tutorials that I've been preparing for a while. And well, probably it's good if we have more information out there. So probably you will see like similarities on his approach and my approach, because basically we're borrowing from the same code. That is one that I simple 3D GAN PyTorch, I think it is. Just I think this is one. Yeah, this is the one. This is the implementation that we're going to use on Colab with some modifications, because this is updated to Python 3. And it's working also with, I mean, what is the problem here, right? This is another implementation of the original paper. Now it's working on Python 3, but it's working with the same math format. So we're not going to use that. We're going to use something that is called Binvox, that has been using for other people. Binvox is a format, basically like a voxelized format. It's basically just a binary 3D voxel grid that tells you that if you have a voxel in a location, it's true or false. So we're going to use this. So in the first part of this tutorial, I will teach you how to work, or how to create a data set on your own. That is important, because right now, most of the things that you do, sorry, ShapeNet, if you go to ShapeNet, this is an ongoing effort to, here they say basically like to create a large-scale data set of 3D shapes. And you can find, I mean, these are like 75 gigabytes of information. You have like planes, you have other things that are not that relevant, like bottles and bowls and things like that. So you will find like a lot of models. So for example, in the chairs, you have more than 23,000 right examples. You have keyboards. I mean, it's kind of weird as a data set. So sometimes, and I'm mentioning this because if you're interested in design, there are like just enough like categories that you can like basically use here, right? Like chairs, of course, because architects or designers, they have a thing for chairs, so that is a good thing. But I don't know, like about knives, maybe guitars, for example, is an interesting example. So we will do something related to this thing. So to start, actually, one thing that we're going to do, we're going to generate a Grasshopper definition. Inside that, we will write a little Python script, but we will use, just to make things like even more simple, we want to use the digital structures plugin from MIT, the digital structure groups. So if we go to digitalstructures.mit.edu, we have some parametric plugins, and we want this one that is called the Design Space Exploration Tool Suite for Grasshopper. So you want to download this from Food for Rhino. I will put the link in the description. So you want to go ahead and download this. It works. It says it works for Windows. I get a feeling that it works for Mac. So let's give it a shot. Probably not everything will work because it has some like .NET libraries, but I think for what we want now, it should work. So I'm just gonna save it and compress this. You might be like wondering why am I using Mac. It's because I love Mac. So yeah, DSE, and for the installation, if I'm correct, we just need to copy everything because I don't see. I mean, these are the things that we want because we're going to use like these tools that are over here. But let's just go ahead and copy everything. So let's copy this. Let's go to our Rhino. In this case, we're going to use Rhino and Grasshopper. So let's use Rhino, Grasshopper, special folders. It's the same thing on Windows. Components folder. Not this, and here, where all my libraries are, I'm just gonna paste this. So hopefully everything should be okay. So let's see if that's. Once you have downloaded the file, we will see, or install the plugin, we will see that there is a there are some things from the DSE, so not everything, but the things that are here are good enough for what we need to do, because we're going to use something that is called the sampler, and I'm going to show it here. And the sampler, basically, it's something that allows you to create, basically to sample a parametric space, and it has some really good tools to do it. So here you can see on type, you can do like random sampling, you can do grid sampling, basically like an order, or you can do Latin hypercube. So let's so if you go to Wikipedia, basically it tells you what it is, but basically it's near random sample nil random sampling, right? It's not like a very like a structure, like a grid structure sampling, but this is good enough to actually create a good variety of data in this case. So that's what we need for our definition. So I will just going to open the definition that we're going to produce, and I'm going to just replicate it so you see it, right? So this is what we're going to do today, and we're going to start with the most simple part. So basically we need to we're going to do a very simple model that is a table. So in order to do that, let's just, I mean, you can parameterize whatever you want, right? That is the thing. Actually, I should do something like simpler. But let's start just, actually we can start just building a cube, for example. Something as simple as that to see if our things work, and then I will show you basically what we have here. Because we need to, at the same time, we're going to write a small Python package that will write the OBJ files. So we will have a lot of OBJ files. So let's start with this. Let's just start with let me just move everything here. I'm going to go step by step. We're going to start by determining a file path, and this file path. Okay, so as I was saying, let's specify a file path. In this file path, we're going to store a CSV file with all the values for our sampling. So let me explain a little bit. If we go to the DSE, if you install this, Windows or Mac, on Windows you will see more functionality. You go to the sampler, and the sampler asks you a couple of things, like the variables that you want to sample, the amount of samples, the type of sampling, as I explained, like random, like in Hypercube, or grid, a seed, basically. If you leave it to 0, it will be unspecified, a file name for your CSV file, and a directory. So we're going to actually connect this here. We'll start connecting this here, and we will select a new file location. So in my case, I will just generate I generated a folder, and you just specify that folder as your destination. So in my case, actually, let me, because I already have some information in that folder. This computer is working a little bit slow, but that's fine. Dataset. Here it is. Just let me delete that. All right. So we have a clean directory. So what are the variables? So let's start simple. Let's just create 3 sliders. Just 3 sliders, and you want to connect all the sliders with the shift. Don't use a merge component, because sometimes that creates problems. So don't use like merge. I know it's a little bit of a pain, and then you put all the variables here, and then you connect here. Sometimes it doesn't work, I found, but that's fine. So let's just do, sorry, I don't know why. Let's just do a couple of things. Let's just call this like width. Let's just call this height. And depth or length? No, depth. Depth with depth, yeah. The number of samples. Let's say we want to generate, I don't know, just a slider, just give a number. We're just going to generate 1,000 samples. It's fine. The type, you're going to specify a number, or just like right click. We're going to do Latin Hypercube. The seed, we're going to leave it like that, and we need to specify a name, so we will call cubes. So just connect just connect this. So let's just create a couple of panels and see what is the outcome from this, right? So if I double click, I'm still missing data. Oh, SID. Let's just create like whatever number, like whatever. Okay, now it will do something. Just organize this a little bit better. So if we have this, we just need to double click, right? It says like it works on double click. So when you do this, you will see that it just creates 1,000 lists with the 3 parameters that we just specified. So it says like it generated data. Yes, it generated data. The data generated is actually this design map. And these are the values that we are going to use. If we open this file, we will see actually what's going on. So yeah, you see, this is just a file named cubes, and it's just sampling this pseudo random sampling of values. And this is pretty useful because now we will use this to actually design something. So we might want to do a couple of things. Let me just clean this because there are things that are not necessary. The first one will be we want to work a little bit with so we want to actually get those 3 parameters to generate like all of our cubes, but the way we want to do it, it's a little bit tricky. Probably there are better ways to do it. This is the way that I found that it's good. So we will just do basically what we want to do is we want to let Grasshopper to generate this automatically. And to that, we will take advantage of one functionality of sliders that is called animate, to generate not only the models, but also like the pictures of this. Because animate basically creates pictures based on our on what we have in our model. So to do that, we will actually do something like this. We will concatenate a panel with open curly bracket. This will concatenate a actually this is yeah, fragments of a text. I was okay. Sorry, usually I use Grasshopper on Windows. I don't use it on Apple, but on Mac OS, but I need to do it now because this is the computer that I have at hand. So this is fragment B. And as fragment C, as you can see here, we will just use a slider with the amount of data that we want to generate. In this case, we want to keep it the same as the number of samples that we created here. So we are creating, for example, like 1,000 samples. So we will just say like 1,000. So we will go from 0 to 1,000. And we will put this here. So this will give us, basically, we can do this by code in an easier way, but we want to keep it like a little bit pedagogical and simple. So you see that this is generating this thing over here. Why? Because what we want to do, our workflow, we will take each time one branch or one like end of our data tree and get those 3 values to generate a model. So I will leave this here and I will leave this here. So if I remember correctly, yeah, we want that. And now we want to get a 3 item. Our tree is our design map, basically like the values that we get. And we are going to use this, this concatenate as our path. and we will play with the index. So in this case, what we want to do, once we have all of our items, so for example here, we have just like here, right? So we have our item, sorry, we have our tree item. We want to get the tree item, but at the same time, what we want is to get our 3 parameters. So we want to do, for example, like series. We want to specify that we want to get from 0 till, and I'm using a slider because then you might want to add more parameters. The step is 1. We can leave it by default, but we're going to use a slider anyway. And count. So this will go to 3. So we have 0, 1, 2 because we want to basically use this to iterate over this. So if we plug this here, we will see that we're getting the 3 values, right? The 3 values of the item at branch 0 at that path of the data tree, and as we move, we're getting the other ones, right? So we're getting this this thing over here, and the last one will be basically a null value. So we want to keep this up to 999 actually. Yeah, so we don't get negative value. So with this, right, we can create our cube, right? So we can say, does this have a cube? Actually, it's box, I think it's called. Box. Again, I'm keeping it like super simple. No, it was, let me see. Oh my God, it's been a while since I used, is there one that actually have play and size domains? Yes, let's use this one. Right, it's a domain box that has a world XY, basically something created in the origin, and we will use the 3 values here. So we can say like list item, list item. This is our list, and we can just add outputs here. So this could be like X, Y, and Z, right? So we can connect this here. Again, in your case, basically, up to here, up to this part here, this is like very mechanical. And this slider right here, right? Number of models to generate. And also the variables will depend, right? They will vary according to what you can add as many parameters as you want. But remember, if you have 3 parameters here, also you want to increase basically the number here, because I'm just using 3 parameters. We will see in this other example here that I have 10 parameters, right? So it's a little bit more complex. So this is why I'm trying to keep it simple, just to demo this, right? So right now, what I'm producing, and actually I have the model here, are just so if we see everything here, as soon as I move, you see we are just generating in the positive like quadrant of X and Y, right? Just like different cubes. One are really thin, the other ones are not, because we're using this nice tool that is sampling, doing the sampling for us. You can apply like random values, but I think this is a very useful tool. And of course you can like, there are like functions, Python functions or C# functions that will allow you to do the Latin hypercube sampling without going through like the installation of this. But yeah, it's there, let's use it, it's good. So in this case, we're creating the boxes. So if we compare it to this, we will do this later, right? What we want to do now is to actually write a simple Grasshopper script. Sorry, not Grasshopper. Grasshopper files are definitions. Code inside Grasshopper is a script. So we will do that. So what we are doing now, actually, we need to proceed with a little bit of caution because we can generate like a lot of data, right? So we don't want to generate something that is like really heavy. We are just producing OBJ files, and for that we will actually use again a small Python script. It could be done in C#, but we will use Python because of convenience, because C#, for example, in Mac is not very good. The editor actually is really bad. So we want to go to Math and go to Grasshopper Python script, and let's just write a definition first, right? Or let's write this. So let's just do, we're not going to use, no, we're not going to use the Rhino script syntax, but whatever, I'm going to leave it there. So we're going to import OS, and we're going to generate or create a definition that will be called export OBJ. And for this, we will need a mesh. We will need also a path, and we will need a file name. We'll need 3 parameters. So let's just do that, actually. Let's just go here, and let's just say that our first variable will be called mesh. It's item access, and we will say that this is a mesh. The second parameter will be path, and this will be a string. And let's add a third parameter that will be the file name, that also is a string. So we'll call file name, and this will be a string. Expected an intended block. Yes, it's giving just like whatever error. So we will use this. Let's just write the script first. We will say that the object file name is going to be equal to, what can we use here? Yeah, I think the format, I should have brought my notes. The format will be something like this. It will be percentage %s, because we need to format the string. Percentage %s, sorry, percentage, and percentage file name, comma, yeah, OBJ. We need to basically format the string so it's in the, sorry, this is like this. Yeah, so we need to just format the string that it will take the file name, and I'm missing one. Actually, this goes here. Is that the right format? Yeah, that's the right format. It will take the file name variable and it will add the extension, so that will be our file name. Here, do we want a material name? Actually, we don't want a material name. We just want to specify an OBJ path, file path, and we will do something pretty not similar actually for the material. In this case, we don't want to export the material. We don't care. Join, and we will use the path and the OBJF name. So basically, this is the path, this is the address in our computer where we are going to use this. So actually, I wonder, just in case we don't get an error, let's just also do the material name. Because I'm not an expert in OBJ like stuff, but basically we need to construct the OBJ in the right way. So I don't want to have like any problems that I need to fix later. So let's do the same thing. Actually, let's just copy this string formatting thing and just call this MTL for material, right? You can delete those later, that's fine. And because we need to, I'm curious about this because we need to write actually a header for this. So this will be, so also this could be useful if you just want to export the things, right? The meshes and stuff like that if you're working with material. So we just need to format this the right way. So you call like Rhino and MTL live, yes, S and G percentage. This is all like, again, like string formatting, like things that are kind of like use MTL. This is because we're just exporting with a diffuse material. 255 and yeah, this is the right format. And just looking at this, sorry, it's only one, and here we'll say that this is percentage, because we're formatting the string. So basically we will do like material name MTL fname, and the name that we are giving will be object 1. I think that is correct. Well, if we have an error, we'll save. So this is the important part. Here we need to say like with open obj file path, and W, like, I think this is for write, yes, as F, we will do the following thing, like F that write header. We need to write the header of the file, and here we will say like for, we can say like for vertex, let's call like this VTX in mesh that vertices, because we're actually writing OBJ, right? We will say like F that write, and again we want to format the string here, so we want to do like v percentage point for F percentage 4.f percentage 0.4f, sorry, 0.4f, 0.4f, 0.4f. Is this correct? Yes. Yes. This will hopefully generate this. You can say percentage, and here we will pass the parameters like VTX dot x, comma VTX dot y, comma VTX dot z. And that is right. So this will write actually the vertex position. So now if we have a material for UV coordinates in mesh that texture coordinates, we can do file.write, same thing again. We need to format a string, so we will say like bt percentage point to f because we're dealing with just two coordinates, percentage to f backslash n, the percentage sign, and here we will just say like the UV 0 and comma UV 1. With it, we should be like okay. So remember that in each like 3D file, we're dealing with the vertices, the UV coordinates, right, for texture, and we're dealing also with the normals of the vertices. So the reconstruction of the mesh is correct, and also we're dealing with faces, right? So that formatting is a little bit tricky, and this is why it's like a little bit long. But it's good that we're doing this. So now let's write actually the normal for vec in mesh that normals. Let's do the same thing, f dot right. In this case, we need to do vertex normals are VA, yes. So actually it's the same thing that we have here. Let's just copy a couple of things. So it's 0.4, 0.4, /n. And here what we want to do, yeah, actually we need to pass the same parameters. So we are good. Yeah, because basically we're getting the normal from this position. So in this case, it's not VTX, it's just vec. That's the only difference. And finally, sorry, it's a parenthesis here. And finally, what we need to do is for face in mesh that faces, right? Because this is the structure of the mesh. F dot right, we will write here just F. I think I'm correct. I'm sorry, I didn't bring my notes to record this video, so hopefully it will be okay. If I'm trying to do this by memory, so we will say like for I in face, because basically like we are iterating over all the faces, so now we are iterating inside the face. F dot right, and here the string will be formatted as percentage %d. In this case is the slash percentage %d. And again slash percentage %d. I'm sorry if I'm a little bit slow because I'm a little bit skeptical of what I'm doing, but if I remember correct, it's like, yes, again, like I plus 1 will be like the first vertices. Everything is I plus 1 actually. It's I plus 1, comma, I plus 1. And then we will see just like F that right and here's just like the N. I think with that we should be okay. F right, F for I in face, F right. Yeah, I think this is correct. And finally, what we want to do, we don't want to actually like, we don't want to return anything as an output from this script. We just want to call this export obj mesh and path and file name. Those are the three basically variables. Here we're just like calling the function. So let's just evaluate this. This is giving me an error, of course, non-type has no attributes. let's see this error in line 68 join 17. Yeah, probably because we're not specifying anything. So I think if we plug our things, it will work. So as you see here in this case, we will do something for our file name, something like very, very simple. We will do again concatenate, and we will concatenate a number with a name. So we can say like here in this like cube. We can say this. Just a panel that has like an underscore cube in it. There, cube. And this will take as the first part of the string the number of the model that we're generating. So our file name will be basically like 0 cube, 1 cube, and so on and so forth. So we will put this here. The path to save everything is the file path that we have here specified. Sorry, I put it in mesh. Stay here. We want to put this in path, and the mesh will be our cube, but we need to mesh it. So basically, whatever we have, we just need to mesh it, and we will put it here. Now this keeps giving me an error. Cannot find unsupported character. Trying to run this. Probably have a mistake. Line 26. Let me see. Line 26. And the mesh vertices. You should not be getting this. Now in line 32, we have another. This is in the mesh normals. Mesh normals. Yeah, I had some errors here. Okay, now we're good. Just had some like errors with some characters, but I think that we are okay now. So let's see actually if this works. Now this is working, and by default, because we are already actually writing something, you can see here you see I have a cube written because we are already like calling this function, right? So what you can do also, like you can put a data dam, so you don't write any file yet. But what I wanted to show you is that this is a very nice pipeline. Actually, let me move this, and then we will do it with this definition here. This is the full pipeline. And what I always do, right? We have the sampling, we have all the information. Remember that you need to double click and create this information first. We will go from 0 to 1000. So now what I want to do is just automate this process. Click on animate. This will generate also like this visualization. That's fine. We don't care a little bit. We don't care about that. So we can actually save this. We can save this in the same folder if we want. New folder, images, open. But now we will just say OK, and this will start going one by one, and we see how our folder is actually full of data and a good data set that we can use for our 3D GAN reconstruction. So this is actually fantastic because we can see that there's like plenty of cubes. These are just cubes. This is a toy example, but the code you can use it with your own with your own models, right? So we will see that this generated, in fact, 1,000, and these are all the models that we generated. This will work Windows, Mac, so don't worry about that. So this is very interesting, and this is super, super, super nice. So we did this with that really simple cube. But what if we want to do it with, for example, something a little bit more complex? So let's change this data path here. This is the same definition. We will say like select a directory, and I will do it on my desktop again. New folder, like this will just create tables. It's just, again, another toy example, a little bit more complex. So if you're like very good at Grasshopper and you know, or basically you know how to establish the definitions and model things, it will be like very simple for you to actually follow from here. So I will just say like open. I will generate again 1,000 examples. Double click. This generated. So this generated again a data tree, with 1,000 branches, but with 9 parameters. So these are our 9 parameters here. We have a because these are generating actually this, like tables, kind of weird tables. I mean, let me just get rid of the cube here. I'm just going to disable all of that. These are tables, right? And we're specifying some parameters, some like number of sides, number of legs, height of the legs, if it has a fillet, and so on and so forth. And we're following the same procedure. So we have a seed, we have the number of samples, we have this that is actually the let's call it like current sample, and here you see before we were just getting 3 parameters. Now we're getting 9. So for each branch we're iterating and we're extracting those 9 parameters, and those are the parameters that we are using to actually create that mesh. In this case I'm creating like separate entities. So then after I mesh the brep, I just do a mesh join, and even though we will have like naked edges and then weld stuff, you can refine it, you can weld stuff. For the voxelization, it doesn't matter, right? So I mean, if you want to be like very refined, and you can, I don't know, go through other processes as well, for example, like use Dendro or any like isosurface generator to actually generate this as an isosurface, so it's continuous. In this case, we don't care. You can weld the vertices, so you have a well-constructed mesh if you're using this for another example, not for a 3D GAN. So the same thing here, we're getting the number of the current sample, we're calling this table, and this is the file name, and I'm using the same Python file. So let's just generate, let's just do the same thing. In this case, just let me right click here, animate. Let's change this to, how did I call this? Tables, new folder, images, create, open, and yeah, frame count 999. Just press OK, and you see that this is generating from the Latin hypercube sampling, like sampling this model. And again, super interesting, because now if we go to the table, as you can see, I'm a little bit messy with my folders, but that's fine, don't judge me. Tables. So we have our 3D models. This has a problem though. In this case, and this is one modification that we need to do, Rhino maps the z-axis, the z-axis, vertically. And usually for all of, like there are others, right, for example, like Unity assumes that z is like depth. and Y is up. So we might need to do one change here that I will do after we finish like generating the samples. That is to actually add rotation. Rotate our model, in this case, I think it should be 90 degrees. Or you can add that. I mean, you want to rotate your model 90 degrees. So basically it's pointing, so you map the y-axis vertical, right? Yeah, so you want to rotate on the x-axis minus 90 degrees actually. So let's wait for this to finish. It's actually pretty fast. We're halfway there. It's taking, yeah. You see the profiler just to generate it and write the sample is like, it's quite fast. We're done with the sample generation. Yeah, it's giving me an error because it's trying to generate a 1001 sample, so that is fine. So as I was saying, one thing that you can do is actually rotate around an axis and a vector. So we can say our geometry to rotate is this one. The angle we can rotate this actually is minus x. I think this is the way it works. Yes, minus 90 degrees. The center of rotation, actually what we can do, we want to rotate over the x-axis. The center is the 0, 0, so that should be okay. Let's just go back to the first example. Yeah, this is okay. So this is rotating in the direction that we need. So basically it's like that direction over there. So then you just need to replace this geometry here. Turn this off, and you want to generate your OBJ files like this, rotated. Again, this is the sample. We will leave it up to here. In the second part, we will learn how to work with the dataset, how to generate the bin box files, and in the third part, we will go into the training, and there will be a fourth part on how to actually use this outside Colab. So thank you very much. See you